Yeah, so I'm Davies. I'm Kotlin and Android DDE in Berlin. I'm currently working on Kotlin multi-platform at SumUp. You'll also notice my lovely cat here, Cotty. You'll see plenty of him. And yes, he is named after Kotlin. Yeah, so this is sort of the second revision of this talk. The first one I gave in DroidCon Berlin and New York called Beyond the Mockery. Basically about my aggravation about people using and misusing mocks. And so I'm going to walk us through a bit of a story, a bit of a kind of role play here, that we have probably faced a lot of times in our careers. So we start off and we have new job. We've got our new computer, we've got all of our new swag, we've got a fancy coffee maker, and you sit down with your new team and ready to start working, and that's when you see your new project. And that's the thing, it's like the luxury of it is the thing of it is we don't have the luxury of working with greenfield projects all the time. Production projects are often quite complicated, often with a backlog of technical debt and things that you just didn't really expect to see. And it can be tough to know where to start with these legacy projects. Legacy code is a topic most common to developers. It's denoting or related to software that's hard to replace because it's so widely used. And the issue with it mainly is because it's uncertain. This level of uncertainty is difficult to kind of work with. It means behaviors are undeterministic, difficult to test, and more importantly, difficult to predict. And it's easy to judge this, but what actually causes it? And this is the concept of coupling. Coupling often describes how interconnected modules are often kind of connected with either coupling or cohesion. And highly coupled code is difficult to separate. It makes it very entangled and kind of difficult to work with, and it's hard to find a seam. I'll elaborate more on what seams are a bit later. Whereas you want to have something that's more highly cohesive, where you've got tight modules that work together very nicely, where they have a limited API service in the way they work with each other. So this means you have less exposure, less risk to the internal implementation of your application. The other thing you've got is inheritance, and you've often probably heard the concept of inheritance or composition. And you've got inheritance, for example, is a complex hierarchy of inheritance with unclear responsibilities, invisible behavior that's often hidden behind abstract classes or base classes. You maybe have seen like base activity or base fragment that you've ever had to work with. These things are dreadful. And it's often an attempt to try and reuse code. And then this code will be moved to an abstract class, and you'll get implementation there that is just a little bit hard to find or a little bit unclear, and it further adds to the unpredictability of the nature of our system. So I'd like to cover as well mutability. So unnecessary mutability introduces changes into our system, and this undetermined change causes unpredictability and unreliability, making it more difficult to assert what the expected state should be. Again, going on unpredictability, unpredictable code is by definition difficult to predict. The clue's in the name, and it's difficult to assert expectations upon that. This uncertainty can be caused by polymorphism, different execution paths, and things that behave differently about different where they go. So this is often like with backup code or unnecessary checks, or often considered as like resilient code, where you're handling things just in case something goes wrong, but it actually creates noise and adds uncertainty to the behavior of your application. I'm going to repeat myself a lot on that. So there are many approaches to manage these issues that are available to us. And ultimately, our job as engineers is to choose the right tool for the job. And one of these things I like to cover is extreme programming. Now, extreme coding practices intentionally take what are considered our best practices to an extreme level. Some consider it like poor use of time, that it takes extra time when they've rather spend time, quick fixing and fix later, and maybe they've got to do a bit of firefighting and fix a lot of things over here. But even if you're not using these practices all the time, it's still really useful to your growth as an engineer to try these things out and know how to use it, know how to use these tools if you need to. A common approach you might already be familiar with is pair programming. Most commonly includes working with colleagues or working with other engineers for a single task. And this refreshed viewpoint is really useful for looking at this task with a new perspective. You can increase your scrutiny of the task and increase the perspective in which you actually kind of would view it, because perhaps your assumptions are wrong, perhaps your assumptions are just different. And having that second set of eyes can be really useful to the way you look at the problem. Another approach is test-driven development. You've probably heard of this as well already. This is where you are writing tests prior to the actual implementation, and therefore you're actually asserting upon the implementation of your class prior to everything else. So this means you really need to understand the functional requirements of your application and understand how it should be doing. So your coding is only necessary to actually solve the tests. You end up with less code, and a lot more times you can avoid the Yagni thing, you ain't gonna need it. And one of my personal favorites is offensive programming. This is another approach that embraces errors as behavior to disprove developer assumptions. You might have worked with like unnecessary checks, having try catches, if then else, and all these kind of safety mechanisms that prevent your code from crashing or your application from crashing. Whereas offensive programming would then embrace that as, if exceptions are happening, then they should be happening. And these polymorphisms, the fallback behavior, the unnecessary checks, these are sort of stripped out, and it makes your code much cleaner, much more easy to understand. And the nice thing about it is that the source of errors are no longer obscured. You might be familiar with that one obscure bug that you had to try and find out and try and find this weird stack trace that you couldn't figure out where it came from. And it turns out it was being thrown somewhere way else in the application. So throwing first and throwing early means that you can catch these bugs much quicker and much easier and find them quicker. And of course, it's much easier to fix something if it's crashing. You can convince your product manager, like, hey, I need to fix that right now because it's crashing. But don't tell them that you made it crash. So I think one of the guiding principles of Kotlin is to make it easy to write good code, to encourage developers to write better code, become better developers. And it makes this sort of slight encouragement by making it poor code a bit more uncomfortable. And I think one of the primary tenets of this is the concept of mutability. But what is mutability and what are the risks of mutation? So taking this highly contrived example that I hope none of you have ever written, you're using an impure in-place mutation. So you're taking in a mutable list as an argument and actually performing operations upon that. Now this is really bad practice because you're mutating the input that you're provided, and then you're going to end up with a different result every time you execute this thing, making it impure. So it's non-deterministic and it's hard to predict. Wrong button. So the date class is another example of this. While it's coming from Java, you might expose it through an API into Kotlin, and the date class itself actually is mutable. So if you're returning this value, then it can be then mutated downstream. This is something that can affect the internal machinery of your application if you're exposing this to consumers. And the crux of this is that you have a shared mutable state, causes race conditions, non-deterministic behaviors, and these risks can be mitigated with like thread-safe confinement, mutexes, semaphores, but ultimately better architecture will help prevent these issues. So you've probably heard the phrase as well, unidirectional data flow, or UDF, and this ensures a predictable state which is easier to find bugs, replay events, and predict your application state. You might have different architectures, MVI, MVVM, MVP, MV asterisk, MV, whatever you like. These are not so important as they're mostly in implementation details, so long as you keep this core fundamental concept of unidirectional data flow. You might have seen in Kotlin, you have these immutable collection types, converting a mutable type to an immutable one, an immutable one to a mutable one, creating a new instance, making that then copy safe. These collection interfaces might also be backed by Java implementations, so they're not true immutable, but they are still representative of how Kotlin tries to encourage you into this immutable state. But if you want to go fully immutable, then I would recommend using the Kotlin immutability library. Immutable collections. This is really helpful with Compose as well because you no longer need to use the annotation stable, and it just helps you have a more stable application. One other thing I really enjoy about IntelliJ, about this immutability concept, is that it actually underlines these little mutable values. So as engineers and as programmers, it sort of gives us that little itch. It's like, something's not right here. It makes me uncomfortable. Looking at this code makes me uncomfortable. So having mutable values all around the place, it looks not great. So it sort of subconsciously encourages you into being better at what you're doing. And as well, you might be familiar with the fact that Kotlin implementations are final by default, so they cannot be inherited. At first, when we moved from Java, this was a bit of a pain, but then we fully embraced this thing and actually used it to our advantage. And that's the nice thing about it, is that it encourages us to use interfaces and interface delegation over the things like abstract classes and classes that we want to kind of extend from, so this composition over inheritance thing. But ultimately, the best tool in our arsenal is testing. The automated tests can act as a safety harness and give you a bit of confidence when you're changing your code. Well-written unit tests can provide robust protection and early feedback against regressions. And poor code is often synonymous with poor testability. So if it's difficult to write tests for an application, there's probably some improvements you can make. So it's not my goal to convince you to write tests. Hopefully, we should already be wanting to write tests. If you're here at a talk about writing tests, I hope you want to write tests. So let's go over how we can make our tests better. So testing approaches can come in many different forms, chiefly manual or automatic. You might have manual tests run by QA engineers, developers, or to verify or reproduce errors. And then you might have automated tests run on a CI that take the form of unit tests, integration tests, espresso tests, UI tests, monkey tests, fire testing, all these different types of testing. But what's most important is that we consider this test pyramid, which you might have also seen before. So a comprehensive test suite is made up of complementative test items. So at the bottom, you might have unit tests, then on top, service tests, UI tests. And you might have more tests in this thing, but the idea is that the quicker to run tests are sort of the foundation that you're running on, offering more isolation, more independent unit testing. And then you might have more integrated components running at a larger scale, which obviously is going to take more resources and run a little bit slower. And it's not until we start writing unit tests that we realize how difficult it is to test our code. And this is often a sign that our code is not structured well, that it could be improved. Most established code bases, of course, have a long and colorful history with changing requirements. And accumulate a lot of tech debt composed of anti-patterns, code smells, and poor decisions that happen during the business process. Sometimes you don't have all the time in the world to have the best solution. Sometimes you have to cut a corner. Ideally you shouldn't, but these things happen. So this is why it makes it necessary to then refactor this code to make the code testable in the first place. But we might find ourselves in a bit of a deadlock situation here, because we want to write unit tests for an application, but we can't write unit tests until we can assert the behavior of the application. And we can't assert the behavior of the application without unit tests. So we have this requirement on a unit test, and we can't refactor without confidence. So how can we refactor code without changing its behavior to make sure that we can write unit tests, so then we can be more confident in the behavior and then refactor? Well, there's a concept of seams where two fabrics meet together, and we're all wearing clothes today, I hope. So you're probably familiar with how clothes seam together. This translates similarly in programming. So there's a logical separation between two pieces of code. And this separation allows you to sort of adjust the behavior without changing the code. There are many different language-dependent techniques of doing so, and I'm just going to go over a few different ones here. So introducing a seam I'm going to focus mostly on object-oriented refactoring. This allows for replacement of a behavior without modifying the implementation, and the most common type of refactoring, and it's utilizing the compiler configuration. So looking at this class, how could we refactor this quite easily in Kotlin? And we would do so like so. So often refactoring, we can make use of idiomatic code features in Kotlin or the language of choice. And the coder just here creates a functional interface with a corresponding factory function. Most importantly, it takes the parser as an argument rather than actually instantiating it itself. This is called dependency inversion or inversion of control, relying upon dependency injection for its parameters. And what's quite nice in IntelliJ is that you can often do a lot of these refactors within a few clicks, just with this automatic refactoring tool. And that can give you a bit more confidence in the behavior that you're changing because it's automatic. You know, you're not then subject to human error, or you can at least blame JetBrains. This is not to be confused with dependency injection. These are dependency injection frameworks like Dagger, Coin, well, not Coin, it's a service locator. I'm not going to go into that argument. But dependency injection is a coding paradigm. It's a mechanism for injecting dependencies into the implementation of your class, not how you do it. Dagger is merely a framework. So looking on our very favorite thermosiphon example, we can see how common refactors to invert control require the caller to provide dependencies. So here we're providing dependencies into Coffee Maker instead of actually having them instantiated in the class itself. And reducing the behavior as well, we can then say we're taking in a pump instead of a thermosiphon. So you're narrowing the dependency scope that has. So pump only has one function. Thermosiphon might have had a more complex implementation. Dependencies injecting into a class constructor. This is a nice thing we can do in Kotlin that actually make up the values of that thing, of that class. But for some tests, you might want to use different dependencies. But why is that? So, for example, it might be considered a bit overkill to use a nuclear fusion heater for a unit test. Expensive dependencies should be replaced on the unit test because you want these things to run quickly. Achieving nuclear fusion is probably a bit overkill. Things about like performance and statefulness things should be avoided because these things are difficult to predict. Disk operations are stateful, can change, and will give you a different operation each time. Further, you've got things like just maybe a bit error prone. You have something that's unbalanced. So it might be good to isolate that dependency under test so that you can make sure that you're verifying the right behavior. So introducing the concept of testables. Now, these are quite common, and you've probably already used them, and they offer simplicity, isolation of control, la la la. Most commonly, you've probably used test mocks. Test mocks are a type of test double that allow you to specify expectations, often used to verify interaction with dependencies. Providing a class and a test with mocks, you'll end up with something like this. So we create a mock for the heater and the pump. Excuse me. And then we run our test. Well, what might happen here? Well, nothing, it fails, because we didn't actually tell our mocks to do anything. Because mocks don't do anything, they're just a reflective implementation of that interface. So we provide this implementation with this nice extensive DSL for building mocks. We configure all the mocks to run, and we run our test, and it works cool. So while mocks might be quite useful to run quickly and just get that out the door and get it done quickly, there's lots of like foot guns and unexpected behaviors that mocks have. They're a powerful tool, but it's easy to shoot yourself in the foot, and they don't scale very well. You will find tests with massive implementations and massive stubbing where you actually look at this thing and think, what am I even testing because I'm building such a complex mock? Because declaring a mock at runtime is quite complicated. When you're constructing mocks and creating spies on objects, this is another one where you will actually invoke that function on that list. So because list is empty, you're calling get even though you're constructing your mock, but it'll actually throw an index out of bounds exception. This is mentioned in the documentation for Mockito, I believe. But it often goes unnoticed. Another one is API sensitivity. So if you take this interface with a mock implementation, and then say, for example, later on down the line, you add a new function to it. And that mock is just going to carry on as normal because it's just an implementation, and it won't actually fail to compile, which is what we want. We don't want it to compile. It shouldn't compile because it's a further change in the interface contract. Another one I've seen as well sometimes is sometimes might be tended to mock data classes. I'm not going to show an example of this. I'm just going to say don't do it. Data classes should never be mocked. They're simple enough classes. They don't have enough implementation to be mocked. Just create the damn object. Another foot gun that became quite fun to observe is default answers. So by default, mocks can return null or for all methods or without stubbing, and then unexpected nulls will throw deep in the execution stack and be difficult to find. So people can be tempted to then use like default answers to adjust its behavior. And this is just bad juju. It's really difficult to actually assert what's going on with this thing. Whilst it might be a bit less boilerplate, it's just unpredictable as hell and just really bad. Please don't do this. So the thing I found quite ironic about test mocks is that they're expensive to create and expensive to execute. They often store every interaction that you have with small aggregations accumulating very quickly. And the authors have optimized as well, but due to the very nature of the way of its operation, it's expensive. You've got this runtime code generation, bytecode manipulation, and reflection to actually create this thing in the first place, which is quite hilarious because we created mocks to replace our expensive dependencies, only to replace it with more expensive dependencies. So you have dynamic mutability here, which is a minimal impact, but on a larger scale, it becomes quite difficult to manage. The unpredictable state is hard for people to understand and hard to predict because you've got this mutable variable there. And that goes on to one of the things I'd like to kind of drill down on is this concept of dynamic mutability. So framework-generated mocks introduce this shared mutable dynamic state. And we should all know that a shared mutable dynamic state is awful, it's dreadful, it's difficult to predict, and hard to work with. So these shared mutable states should feel uncomfortably bad. Dynamic runtime declarations should feel equally uncomfortable. And somebody once told me that test code is production code that doesn't ship. So we should hold ourselves to the same level of standard that we would write with production code. This is Cotty again, being very judgmental, because he's a little diva. So predictability is an underrated metric. Much like tech debt, it's difficult to quantify. It's going to have an impact when you're onboarding new colleagues. It's going to have an unpredictable learning curve. And it's going to have problems when you come down to peer review. Because hard to review code is going to stay there for a little bit longer than it should do. So PRs remain open for longer, sad, and alone. What's more is that you have this risk of bugs. This unpredictability means you cannot predict the edge cases. These things are just going to be unpredictable as hell. I've said that 1,000 times now. But much like technical debt, it must be repaid. This slows down feature development. And this is one of the best argument you can make to product managers, to engineering managers, that these things are slowing down feature development. It's making your job day-to-day harder. So we have to make sure that this work is actually paid back so that we don't have these problems. And the victims of this are not just new engineers or junior developers. These are you in the first place. If you've ever come back to a project after the weekend and see your own code and think, what the hell was I doing here? You're not alone, of course. I do this every week. And there's a nice article from the Google blog Testing on the Toilet, Don't Mock Classes You Don't Own. This is a really nice concept because the idea is that if you don't own the class, you can't own the contracts that it has. So then that third-party developer might be then changing the features in the future or something, so then your mocks are then not going to be the same. And it's not exclusive to classes you don't own, because here's the thing. You don't own your code. It might be a naive assumption to think that once you've written your code, then it's yours, that it's your baby, it's your thing to fight and be proud of. Whilst it's great to be proud of your code, understand that once you commit your code, it belongs to your team, and it's your responsibility to make sure that it's understandable, that it's good for your team, because they will have to understand it too, and then you work better as a team together. So if your code introduces cognitive complexity, it's not clever code, it's not smart code, it's just difficult to understand. There's credence to the argument, keep it simple, stupid. So the biggest problem with mocks is that they verify the interaction, not the outcome. And it doesn't matter if the invocation is correct, if the outcome is wrong. At some point, you're just testing the language. You might have seen this when you have implementations like verify this function was called. It's like, I don't care if this function was called. I want to know how that modified the state of my application. So verify the application output state rather than that something happened, because that doesn't necessarily mean anything on its own. This point deserves its own talk, but I've got a lot to cover here. So if mocks are so bad and we shouldn't be using them, and with mocking libraries with all these extensive DSLs, we're building runtimes declarations, how instead can we build our test doubles? Well, what else has an extensive DSL for building classes? Kotlin. We don't have to use mocks. We can create stubs. You might have already encountered stubs. They're simple implementation only meant to help the compilation process. It's the most simplest implementation possible, no verification logic, just enough to get the compiler running. And the implementations can be a bit more idiomatic with Kotlin as well. Here we have a functional interface, and this single declaration here makes the whole mock declaration redundant, which is quite nice. We have classes declared in Kotlin which are sensitive to interface changes. So I said earlier that if perhaps an interface then has a different change in its behavior, the mock will still compile, and this is not what we want. So if we have a stub, for example, and then we change the implementation, the stub is not going to compile because the expectation changes. So this means we're not reliant upon a third-party framework to actually build our mocks, and we know this because we wrote our own stub, so we're then not reliant upon it. But what if you need a bit more than a stub? Well, you still need to verify some sort of behavior or set the outcome of the operation, perhaps. Well, you can then provide your own implementation. Again, test code is just production code that doesn't ship. So you just create a fake pump, for example, or an in-memory storage for a repository or something that you can then keep hold of the inputs and the outcomes and then perform any operations that you need to do. And you have full control over this, and you're using the idiomatic Kotlin language that you wrote the interface in the first place with. So you don't have this confusing mock setup. You have clear idiomatic code that you can then easily understand. And because you have full behavior control, you can then add additional testing behavior that you might need to verify your behavior. So here we're using provided instance as an interface delegate. Very nice feature in Kotlin, which is quite powerful. So fakes are ideal because you define the behavior. And you might be thinking that, oh, what if I have to define this behavior every time I'm writing a new implementation? Well, who is responsible for writing this implementation behavior? Well, that's you, because you are the most qualified person to write that test fake, because you wrote the implementation or you wrote the interface. So you will then be in the knowledge, will then be in the context of knowing what it should do, why it should do it, the purpose, and then why it's there in the first place. You are the most uniquely qualified person to write that at the time, and therefore you should do so. Because at the time of authoring, you have that context. This goes for library authors too. If you're developing a library, it's very useful to be able to ship a testing artifact at the same time. And in many circumstances, it's enough to actually provide just an in-memory implementation. This is sufficient. Given the simple store interface, we can implement this in memory very easily. And what's nice is that we can also use this implementation for debug variants, for example, and have some backup behavior. So ultimately, we can make the argument that Kotlin encourages us to make better decisions by better practices, by making poor decisions uncomfortable. And better practices encourage us to write smaller interfaces and better code as a result. One thing I would like to compare as well is if you're still subscribing to the whole solid design principles thing, a bit of a tired trope, but this one still remains true. Interface segregation, and this is where you should never have to actually depend on a functionality or behavior that you're not actually using. So you might have a bloated interface or a bloated contract there that you need to then implement all these hundreds of other methods just because you need that one. And if you're working with Android, you might be familiar with this concept of context. So like many legacy frameworks, Android has a long and colorful history of legacy code. There have been a lot of advances with Jetpack and Android X and Project Mainline. And these things have improved it, but we still have to work with context in a lot of operations. And the Android context is considered to be many as a God object. God objects often reference a large number of distinct types or unrelated methods. Since they command so much behavior and so much implementation, it's difficult to provide a different alternative implementation. There's no way in hell you could create a fake for this. So that's why often you will have to resort to using a mock. You can, of course, encapsulate usage and responsibilities into individual responsibilities. That's one way of managing it. So to recap, it's important to consider this as another extreme coding approach. Like code katas, TDD, or offensive code, it's really good to practice. And you should choose the most appropriate time and consider all your options and all your tools available to you as an engineer. Avoid, like the plague, a shared mutable state. Rely upon immutability. Your goal is to achieve a unidirectional, immutable data flow. This is like the gold standard. It doesn't matter if you're using MVI, MVP, or whatever MV framework that you think is most appropriate for your project. Just make sure you have a unidirectional data flow. And mocks are designed with APIs to verify interactions. They perform black magic, voodoo, Java reflection. If you look under the hood how mocks are actually created, this stuff is crazy. And there are spies as well, which are mocks on real objects. And you have stubs as well to perform the bare minimum, allows your test to pass, and fakes are hand-coded to implementation used for testing. So use the right tool right tool of choice for your project. Make sure it's working, and like I said, avoid mocks, please. And that's everything I have. Thanks. Some further reading as well. I'll share the slides online later.
Thank you very much. Ashley, okay, let's have a look at Slido, if you posted some questions. If you haven't, go to slido.com and use mdevcamp as a handler to get in there. We do have a question. Writing and maintaining tests takes time and effort. Would you write tests for every app and use case? How to find the balance when it pays off?
I totally understand this. It can be a difficult ask to get people to write tests all the time. And it's important to see this as an investment in your own future as well. So yes, it's going to take a bit more kind of investment at the start. Yes, it's going to take a bit more time and effort. But it's also allowing you to kind of hone your skills and to kind of practice these things. Because often you might see unit testing as just like an only cause for regression testing or only cause for safe backup. But the reality of it is, when you're writing unit testing, it allows you to kind of see the imperfections in your own code. You might then think, oh, it's actually quite difficult to write a test for this case because it's difficult. Well, in that circumstance, maybe you can actually make an improvement to the architecture of code, which then improves the readability, improves the scalability of that application, and then results in better production code. So yes, it can be difficult to make this argument. I've got like a big shed load of backlog that I need to deal with, and I've got all this production code to deal with. And you have to then make that argument whenever you can that I'm investing in my future here. I'm investing not only in my time, but for the time of my fellow engineers who are then going to read my code. And then you can make the argument as well that, well, if I'm investing this time now, it means we're going to get better feature development speed. Things are going to be a bit quicker to implement. We can have more confidence in our regression testing, and we are going to save more time in the long run. So it's all about the long vision, I guess you could say.
Okay. We do not have any more questions, but if you want to ask Ashley something, he will be at the speaker's corner in front of this hall. Thank you very much, Ashley, and thank you guys for coming to this talk.